So today we will learn about locality of reference. So as the name suggests, locality means neighborhood and reference is the CPU's reference made to the main memory. Here we will consider it as RAM. This is one RAM. It actually means whenever a CPU is making a request in order to fetch some data from the RAM, then it will show a tendency to access the same particular block or the neighboring blocks from the RAM. Assume that whenever it is accessing data from this block, there is a high tendency that it is going to access data from the neighboring blocks or the same block. So in order to tackle that, they fetch the block along with the neighboring ones. So there are two types of locality of reference. One is temporal, one is spatial. Temporal is based on time and spatial is based on space. In temporal, if this means that for the first time we have accessed this part, so in the upcoming time only this part is going to be accessed again. But spatial says that if this part is being accessed, then there are high chances that these parts we'll consider soon. Now an interesting question arises that what is the use of this locality of reference? Why we need it? We need it because when CPU wants to access some data from the memory, and there are chances that it may not be present in cache. For that reason we have to travel to the main memory and fetch that data. So whenever we want to fetch that data again, there are high chances that CPU is going to need the neighboring data or the same data again. For that reason we use this locality of reference. Whenever, for example, we need this, we'll fetch this from main memory to cache. Along with that we'll also fetch neighboring blocks as well. This will help us to increase the efficiency because we know that it takes significant amount of time to move from cache to main memory, fetch the data back to the cache, then again to CPU. However, we can reduce this time if we put some amount of predefined data based on some calculations which CPU does, and we fetch the data which can be predicted that CPU will need it into the cache. So it will take this much time only. Now talking about the cache memory, as we already know that these are the parts of CPU which are very high speed memory, where the read and write thing happens at very high rate. So this will increase the efficiency as well as reduce the access time if the data is already present in the cache. Now how this cache works. Now in order to understand how this cache memory works, we need to understand some terminologies which are cache hit and cache miss. As the name suggests, that in case of cache hit, we are getting the data which we need is already present in the cache. So we'll travel from CPU to cache, fetch the data back to the CPU, the work is done. However, in case of cache miss, the data is not present in the cache. We have to move to the main memory, fetch it to cache, then it will transfer it back to CPU. So another terminology is hit ratio. It says the number of chances the data required by the CPU is already present in the cache. If I say that the hit ratio is 80% or 0.8, means the cache will return 8 times correctly for the 10 requests made by CPU, and for the rest 2 it will have to go to the main memory and fetch the data, and the hit ratio will be in this range. The formula of hit ratio is the number of hits divided by the total number of references. So it says that if the CPU is making 100 references or 100 requests for data, and out of which 80 of them are fulfilled by the cache, then the cache memory is having a hit ratio of 80% or 0.8. And in a similar manner, miss ratio is the opposite of hit ratio. It is pretty clear that in when we are asking for hit ratio, we'll consider cache, and for the miss ratio, it means that cache is unable to fulfill the request or the reference made by the CPU. Hence, we will refer back to the main memory and fetch the required data. Now, the another important thing is average memory access time. It means that the total time taken in order to perform all these tasks, like whenever a CPU is making reference, if it is already present in the cache, then it will return the data back to the CPU in a very simple manner. However, if this is not the case, it has to go to the main memory. So the average time In order to perform all these things, the memory access time for each hit, if the data is present in the cache itself, we'll multiply it with the hit ratio, and then for the miss ratio, we'll multiply it with the access time for the main memory, and we'll add these two up to get the T average, the average memory access time. Now we have seen a general formula, but in few special cases when there are two different type of cache access techniques, which are simultaneous access and hierarchical access. In simultaneous access, the thing happen is that CPU, instead of finding in cache only, it goes to cache, it also goes to main memory, and they fetch the data or make the reference in a simultaneous manner. However, in hierarchical access, it first goes to cache, then afterwards it goes to main memory. So there will be different formulas for each of them. For the simultaneous access, we'll multiply the hit ratio with the time required for access in cache memory, and we'll multiply the miss ratio along with the time required to make the reference or the access time of the main memory. However, in case of hierarchical access, we are taking extra time because we first find the reference made by the CPU in the cache. For that, we'll multiply the hit ratio with the access time in cache memory. Afterwards, for the miss, we'll add the access time for main memory and cache memory and multiply it with the miss ratio. This is the simplified version of this formula. We have removed this h and only taken in consideration up to this part. This is mathematically proven, and this thing reduces the calculation.